Marcus is a TAFE teacher, but he also seems to have a finger in a whole lot of other pies. And he can probably tell us a little bit about that himself. So I'll pass over to Marcus.
Thanks, Anne. I'll get my screen shared. Okay, good. Look, my background is design and a little bit of CAD. And I used to teach perspective drawing and that sort of area, and got into the digital side of things. And eventually, because of my background with CAD, the college asked me to teach 3D printing. And it was a bittersweet moment because 3D printing can be very exciting, but the plastic issue never sat well with me. And so it was always on the back of my mind to try to do something about that. And eventually I got some money from the council. I was able to buy a few bits of equipment. And yeah, so it took from there. I should show you some examples. I'll stop the sharing for a sec. And I will show a few examples of items that I have been successfully producing. First thing is to understand that, well, basically we have a lot of plastic, of course, but in Tasmania particularly we have a lot of rope because of the aquaculture industry. And so I decided to focus on rope. Rope is very abundant and very difficult to tackle. And I always knew that the digital fabrication, you can produce stuff locally. So I thought it was a good pathway. And it's becoming a good pathway. But it's very difficult because to start, we have to grind the rope. And to grind the rope, you have to do a lot of passes, and it tends to jam and to tangle. So that's one stage after passing through the grinder 4 or 5 times. And this is about 10 times passing, and eventually want something like very fine and very, very minute. But that takes a lot of time and energy. So we hacked into a few other machines and had some success. I'm talking about many, many hours tinkering. And anyway, long story short, we managed to produce an item from the 3D printer. And just to prove that can be done. And we haven't progressed a lot other than got some excitement from the mainland and managed to get a group going. And we found a group, well, actually a big rigging business in Victoria approached us as they was the only people in Australia that is doing some stuff with rope particularly. So that's exciting. It's giving us a little bit of momentum. So I have a group together that is helping along, and everyone is doing a little bit, but it's a slow process. The plastic crisis probably will help activate a little bit more and maybe getting a bit of fun. But I'll just show a few examples so people can have an understanding of 3D printing. I don't know what is the general knowledge, but that's how this stuff comes out of the machine. And you can see some black parts of it, and the white is actually the item we want. The black suspends or scaffolds the white bit. So this printer works with 2 heads, and because everything is at the melting stage, you need something to scaffold, and that's what the black does. Eventually, the black is removed, and you have the item with gaps and holes if needed. So that's basically a buckle, and that's the bigger version of the same buckle. So that's a beauty of 3D printing, because one can resize very quickly. As much as you can resize any digital item, you can resize a 3D printed item. It does interfere on the quality of the item and on other features, so you have to be aware of that. But it is very convenient for that. But 3D printing is very slow, and so we are trying to advance into different areas. And 3D printing is just part of a bigger range of technologies. It works well with other technologies. Like this example here is a combination of 3D printed frame, which is slow but is complex, and laser cutted panels. So if we can upscale this type of system, we can pretty much produce anything in a combined approach between the 3D printing and the laser cutting. So I'll just move on and talk a little bit more. But depending on how you design and how you produce the part, you have interesting features. Like 3D printing can be very fragile, but depending how you do it, you can achieve some good result. This is plastic, obviously, but we can do that with different materials. Another example here is this little bottle, which is very complex and very pretty, but because of the geometry, it is only the thickness of an eggshell, but it's very strong. You cannot easily crack it. That's because of the geometry. So this is part of the skill, to know how to design and structure your design. Sometimes the software can help with that. Another example, which is very nice, is this here, which is, again, the printer with two heads. So the inner plastic is recycled, so it's a little bit rougher, and the outer is a new plastic, so you have a veneer with better quality. So that's an alternative. So you can fill 95% of the volume with a lesser quality recycled that can be strong enough, is structurally sound, or you can veneer with a new plastic. So that's a good solution to minimize new plastic. And simple things like adapting. I have a Dyson vacuum cleaner, and I needed a longer hose, but I didn't want to pay the $100 from Dyson, so I just create an adapter that I can plug onto a hose from the tip shop. So things like that can be very useful. People have seen houses being built with a 3D printer. This is a ceramics model made from a 3D printer. So they are upscaling to producing houses, and that's making very exciting. Now back to my little bottle. The lid, I'll take the lid off. The lid was used as a model on a type of lost wax process, and we produced the same lid on metal. Eventually, you chop that top off, and you have the lid. And that's very useful to convert a plastic model into metal. Of course, there are printers that are printing straight onto metal, but that's very expensive, and that's an alternative. One student took a photograph of the art school and convert the photo into cannot see very well, but convert into a 3D model, and then produced a CAD drawing, produced a negative, and then produced chocolate pieces from that. So you can buy a 3D printer that actually prints on chocolate already with chocolate, but alternatively you can produce negative patterns, and she's doing a little business out of that. What else can I show? You probably have seen a wrench made from a 3D printer, and that wrench is obviously plastic, but there are printers doing in metal, and that wrench comes out with the black scaffolding just in one go. Eventually you clear the black, and it's a functional tool. So I'm just assuming you haven't seen much of that stuff. But 3D printing can do things that are almost impossible to do otherwise. This is a 13 spike star. Don't ask me why I did it, but you can not very easily do that manually, or the mathematics involved is quite complex. To have the weight and space equilibrium is quite difficult. So there had to be a software had to be created, or a little code had to be created, and then I can fit exactly what I want. So that's pretty much impossible to do otherwise. Things like this, and that was printed in one go too, but then you assemble. But that's a telescopic system, and straightforward is done. Anyway, I can go on a bit, but I'm going to start sharing my screen because I just have to show a few other, because 3D printing is very engaging, very exciting, but is mostly an auxiliary tool, and we want to use in combination with other tools and other knowledge is part of a suite of technologies, and that's when I moved on from 3D printing to understand the other machines, and that's how I came across Fab.city. So, and Fab.city takes the whole knowledge to a more holistic and a more like, instead of the fabrication of whatever needs we might have, more considering the city needs and trying to bypass some of the environmental problems we have. I'm going to share my screen to show a few examples. So I imagine you can see a blue ribbon on the top. And this is just our website with a lot of examples of what 3D printing can do. I'm just going to scroll quickly. And there are many exciting things. You probably have already seen some of the things that 3D printing can do. I'm just going to go to the bottom, which has a very nice example here. It's Atomic. And that business was developed by CSIRO and a couple of businesses in Australia, in Victoria. And it's becoming very successful. And actually, the uniqueness of this business is that it produces additive items with room temperature, so it doesn't need heat. Is by blasting the molecules or the particles on each other and creating a fusion at cold temperature. So this is unique worldwide. They have a global pattern, and it's very promising business. Very expensive printers, but for high-end metal, heavy items is very adequate. I'm going to try to play a little clip just to give you an idea of a completely new system of printing.
Show 2019. What we have here is a fixed-wing drone, which is some work we're doing with RMIT. Basically what this one's about is a slightly different than normal, basically a drone that works off helicopter type of waves. It's a fixed-wing one. So we're producing this out of titanium. It has significant advantages over carbon fibre. It was quite an exciting project we're working with RMIT and their advanced manufacturing centre in that area. Okay, to add further what we have on our stand here.
I'll stop now. And I'm just going to go through a few examples. That company is very promising and is a high-end. Can produce parts up to 9 meters long. Very exciting. The more you find out about, you see they are really promising a huge breakthrough. And I even bought some shares from the company. This slide you're looking at is showing some 3D printed items on plastic, but they've been restructured with carbon fiber. And the way you do that, you can produce strengths comparable to metal, to some of the metal. So it's competing with metal parts. So that's very promising, and some 3D printers are producing this case here we did by hand, but some 3D printers are doing the layer of fibers automatically. So that's very promising. That's our group of thinkers here in Tasmania, and that's Oscar. He's producing some plates of plastic from rope, and so he's tinkering at the back of his house, his workshop, and so he's coming up with something. And that's from the same rope, so bypassing the grinding or grinding less, and then he's just tinkering at by himself. But we're approaching a company locally to see if we can use one of their presses to produce a little bit bigger format plates and see if we can use for laser cutting. And then we can start making some quicker and more interesting products. Another clip this time is, so this is an introduction to Fab.city. So Fab.city started in 2014, more or less, in Barcelona, and the clip will explain itself, but came from the concept of fabrication labs, and fabrication labs pretty much came from Massachusetts Institute of Technology in the US, and there are about 3,000 fabrication labs across the world. But Fab.city took their concept to the city to try to solve problems with the city to have an impact globally. Anyway, the video is big. It only goes for a couple of minutes.
When you click that button, you're committing to the next 40 years of Barcelona becoming the world's first self-sufficient city. Are you ready to push the button? Yes. Ready, set, go.
When production becomes accessible to people, we are changing the whole framework in which we have been building our society in the last maybe 200 or 300 years.
If you want to be the best, you got to move and motivate.
When you acquire the capabilities of producing stuff, your whole role into society is kind of reshaped.
Technology and data should serve the people. They should give them back economic and democratic control.
At the heart of Fab.city is that atoms that are heavy should stay and move locally because it takes energy and resources to move them around. But bits can go globally. To me, that is a leap in industrial design that works with and within the cycles of the living world.
Fab.cities is not just about a transition of a piece of infrastructure. It's fundamentally a transition to a different economic, societal revolution.
So Fab.city, what changes with Fab.city? It is the response to globalization, and we know, many of us know the issues with globalization, but nobody really knows what to do about it, or the efforts we have done or we try to do. Often we get stuck with issues of competition and government, etc. So the approach of Fab.city is from the bottom up, from the councils, and from the ground up, and that's a very promising approach. So instead of globalization, which is pretty much has subsidies, very compromising subsidies that were pretty much out of reach to us, we are looking at localization, which is the exchange of information, global knowledge, but local solutions, local production. So you can see on this schedule here, instead of the IP abuse and secrecy, we're dealing with open source and transparency. Instead of the labor, the abuse of low-paid labor, and including technology abuse, we're working towards a community approach to information, automation, and robotics. The tax rot and monopolies, which is often done outside our reach and at high levels of government, we can manage better by producing models of production and businesses that are more local with local government. And the environmental abuse, which often subsidizes the low cost of products, is very hard to beat. But if you automate and produce locally, and you start to recognize the costs that are embedded on those cheaper items, we can compete, and we can with the automation we can compete against low labor costs. Social and cultural disruption can be overpassed, and the huge problems with transportation, the fossil fuels, by of course producing locally and viabilizing local capabilities will bypass that. So it sort of pretty much closes the circle all the way to the minimizing items coming in. So we've reduced the amount of waste, and we can justify reusing the materials for our circular economy. That's very important to see those. We can go through each of them, and Fab.city has the whole background knowledge and examples, everything published, and lots of open source solutions that we can discuss for a long time. I'll just move on. But this is a good. This is a good. Again, I'm going to show.
This is this morning. Check this out.
This was an effort here in Hobart, and this is a bit of a case study. We have this group of people in Hobart doing printing face shields for the COVID, and you can see 10 printers going at once. Tim Leonard is, you can see his name there. He's the person who was coordinating all the effort. And that's a beautiful local story where we can see how 3D printing can be quick a solution for an emergency or for the production of items that immediate needs. So the designs were downloaded from open source, and they produced 1,000, or they passed 1,000 shields. And those personal protective equipment are in crisis. The access of them is problematic at the moment. And in Tassie, we were such a small population, we had issues with that. So imagine the big cities. And that's what the people in Fab.city, I had a quick look, and for mass production, they supply you with examples of modes, so you can actually download those files, and you can produce from a laser cutter. You can produce the set of jig, and you produce a mode, and the mode can be produced from recycled plastic or from new plastics. So you have all the knowledge there, and obviously you can just as well you can buy. So they have the open source knowledge, but also you can buy already made if that suits. And also looking through the Fab.city resources, I found from MIT, I found the example of a shield, and I'll just show here, and I'll turn the volume up now. But this shield here, the good thing about this shield is that it is one piece of acrylic, and you don't need the frame, and it's more flexible, so fits different size of heads, and you can lift at once. So it's very, very well designed, and to produce, you can produce on either a laser cutter or just stamp cut them with other machines that can produce thousands per hour. So interesting solutions that are all open source and ready for production. Fab.city is not only about fabrication, but also about the goods we eat, about vertical farming, about automated permaculture. This is an example of a simple veggie patch, and using 3D technology to monitor, to irrigate, to do a variety of things. So that can facilitate and make our life more interesting and a little bit easier for the ones less of a gardener like myself. Many articles coming now with the COVID scenario and talking about sovereignty of Australia. So time has come for us to take more seriously all those alternatives and have a conjoint approach. And if you look at the other cities that are already doing Fab.city, we have a lot. We can just quickly join the bandwagon. This is an example in Tasmania where building boats was a strong industry in Tassie, which sort of suffered from the overseas competition, and now it's coming back, and digital fabrication is helping with that. You can see the CNC at the back here, and digital fabrication facilitates and minimize the costs. So that's very, very important because there's no other way we can compete in some of the industries. Many examples, if you look at, for example, photography, used to be the photo labs, they left the Tasmania, they couldn't justify, but eventually they came, those booths of developing photographs came and you don't need to send stuff overseas or to the mainland. And the more we understand those machines, the more we can hack into them and we can do ourselves. And we don't have issues of labor costs to compete. That is a CNC kit. Is you buy for $500 US, and you have to have a router, and you set up. It's a bit of a headache to set it up, but myself and my partners, we bought one of them, and yeah, very useful, very convenient, and lots of it's called Maslow, and lots of resources to work from, and that house was built from a CNC machine. Many things. Tiny homes produced by a CNC from the back from a garage. I can foresee kids in schools playing with a CNC and producing stuff for the school, or students producing their pods, their small sleeping pods or study pods. Lots of clever designs and jigs that can be simply downloaded and reproduced, rescaled, or utilized straight up. And if it's not perfect, it can be beautiful, and lots of art being produced with digital fabrication. Very exciting and very organic. That's an example of 3D printing, making the joints and componentry. That's very common practice in 3D printing. And again, you can restructure with carbon fiber, or you can convert to metal. That light shade was laser cut from cardboard, and we bought for our home, so produced locally, very straightforward. And I was involved with the design of a light shade, and we convinced a local business to order and produce locally. And that's my workshop. I was playing around with a sample of it. And the same concept producing. We had an opportunity to compete with importation of desks, and we came up with this design and produced 100 of those locally. So we couldn't do that in the past without these new machines and technologies. So where from here? Well, one step that would be nice would be to produce one of those chapters in Renew or Fab.city. That would be nice. So we can start with placing examples and articles that can be useful locally, and some items that can be bought and produced locally. Fab cafes, those are becoming very popular, evolved from Fab Labs and part of Fab.city vision. And you see them in many big cities. And basically is a place where you meet people and you discuss designs and you have access to some of the equipment. And you pay a membership or you pay per use. And it's really cool. Over a coffee, you can do stuff, engage with people, and produce stuff. The tip shop would be a great place to have a fabrication lab, to have a few of those machines, and we can add value to. They already do a great job, but we can add more value and justify recycling even further. Also, the businesses, the local businesses that are already in digital fabrication, they can help us with the education side of things, or making open once a week or whatever for the members, and create a workforce for themselves and create opportunities for their business, at the same time opening up for other newcomers. That's a business in town, Chanderware in Muna, a digital fabricator. DigiLabs is an initiative from TasTAFE, and they have 3D printers and other digital technologies, and they've started on the right foot, but we can go a little bit further. I started a Fab Cafe here in Hobart. It's a simple concept, but it's ready for business, and the same concept that you saw before. And basically, I'm offering myself, if a business books for a function, once we can do that again, we can function, say 50 people, whatever, we can justify doing a consultation. So during the function, we can meet some people in the business, can talk about their procurements and their product range, and we can see what they can replace importation with and what they can offer to the community or elsewhere, and part of the whole scheme. So that's my effort, and yeah, that's pretty much it from me. So I would like to introduce Klaus. Klaus Stroehl is an engineer, and he's very competent in the area of CAD, and so he's going to introduce us to building information modeling. And I welcome Klaus to start. Thank you very much. I look forward to listening to some of your questions.
All right. Thank you very much, Marcos, for your presentation, for handing over to me now. I think if there are any questions in regards to Marcos' presentation, we'll be happy to answer them at the end of my session. So, yeah, I'm not quite sure why Marcos got the idea that I can contribute to this session tonight, but Marcos is very involved in digital fabrication processes, and I'm very involved in an area called building information modeling, which is facilitating digital design and fabrication processes in the building industry. So I hope my part's going to be as interesting as Marcos, and I hope not to disappoint him. So I'll introduce you to the concepts of BIM now, and thanks very much for providing the opportunity to do so. I think I need to switch over to my screen first. By now you all know what I look like. So quick introduction about myself. So I'm a director at a company called Gandy Roberts, a local engineering consultancy. We do all sorts of engineering, and my particular contribution is in the area of BIM Consulting. We're providing training and implementation services for other consultants as well as architects and building designers. We're helping companies to model buildings, so we're providing modeling services, and we're helping project deliveries using building information modeling, and we're managing all of those services, all of those processes. I'm going to explain more what BIM is shortly so that you understand what we're actually doing there. So we're also helping builders and contractors who are using BIM on their job sites. To start with, just a few examples of where BIM, building information modeling, that concept has been used locally in Hobart. The first example is the Hedberg project from UTAS. That's the UTAS Performing Arts Center, which is right next to the Theatre Royal. Most of you would probably know where that is. It's a very, very complex building, and BIM was introduced at a late stage of the project. However, we managed to model all building structures and all the major building services in this project. We coordinated all of those and the builder constructed the building using digital processes as well. So one of the prominent examples here is the CLT panels that were used in the performing spaces. You can see the top right image on the screen there. That's the interior of one of the performance spaces, and they are built using cross-laminated timber panels. They were fabricated, unfortunately not in Tasmania, because until recently there was no CLT plant here. But the concepts are the same. So they were modeled, including all the openings for ventilation, access, and all the protruding structures. The data was then sent to fabricators where the panels were produced as per those design models. They were then shipped to site and installed like a kind of grown-up Lego system without much, any big dramas in terms of the panels don't fit, or the services that have to protrude through the panels can't be connected. So all of that was resolved digitally, then was fabricated according to the digital model and installed. Another prominent example that people won't see as much, but that was probably the most integrated BIM project in Tasmania so far, was a salmon growing facility. So it's a land-based salmon grow out facility in Port Ewan for Ewan aquaculture. Again, this is another example where BIM was used to overcome some of the complexities of the project. I'm not sure how well you can see the bottom there. It's full of hydraulic systems. There are very large precast tanks that we designed. All of the concrete structures there are precast panels, and all of those over 500 precast panels, they had lots of openings in them to get the water inside those tanks and from one tank to another. And all of those openings, they had to be precast into the panels. Those openings couldn't be cut on site through core drilling to ensure water tightness, which means that the whole systems had to be pre-designed, pre-modeled, and verified before we could ask the fabricator, right, we need those panels, here's the panel list, and that's where we need the openings. So I'm going to show a live example of that a little bit later. But before we get to that, I want to just quickly explain what BIM is in less than 3 minutes. That's going to be a huge challenge. So usually it takes me about 90 minutes in a presentation to explain all the nuts and bolts of BIM and how it can be used. So I did take some notes, so I hope I'm not going to miss anything, but BIM is really it is aimed to improve collaboration and coordination on building projects. So it's helping project teams to collaborate better and to produce more coordinated outcomes when compared to traditional plan-based design processes. that are traditionally used in the building industry. So what that means essentially is we'll replace the common 2D planning processes with a 3D model-based approach. This could be as simple as just exchanging some 3D models within the design team. Like, let's say, a 3D model provided by an architect that includes relevant specifications can just continue to be used by, to analyze energy performance, mechanical system requirements, and costs by an engineer or by the quantity surveyor. Another example would be to use the models that are then produced for simulations of the construction activities, to do construction sequencing, or for maintenance schedules for facility management and building operations later during the operational phase of the buildings. So through this integrated 3D process, integrated 3D, using those 3D models through an integrated process, we're achieving a much higher integration of the planning, design, and construction processes, which does open some very good opportunities to design and build better. In short, so BIM is not really a 3D model as such. It is rather a process. And instead of dealing with a mess of plan documentation, which we usually do on our more complex projects, but also on smaller, more simple projects, we use a consistent set of 3D models to visualize, analyze, and develop designs, all the way from the concept design stage to handover of the project to the client. To give you a bit of an idea about how it currently works, yeah, we could say that all of what I've just talked about sounds sensible and clearly, yes, we're in 2020 nowadays, and digital processes are standard everywhere, in particular, or at least in all the professional services. However, that's certainly not the case in our building industry, at least not in Tasmania. So, and there are a variety of reasons for this, but one of the key reasons is certainly that project teams are rather complex, as the diagram is showing. So usually it's not just an architect, a client, and a builder that is involved in a construction project. There's so many more, like surveyors, the clients, councils, quantity surveyors, etc. And that's only during the design stage. We then have fabricators, logistics to build the buildings, and then post-construction, we may want to do renovations, etc. So many different parties are contributing to a successful project, and all of them are using different software, and all of those softwares are generally not, or they're not necessarily compatible, and we don't really know how to hand over our information in a digital format so that all the other parties that are involved in the project, how they are all able to consume and utilize my information efficiently. So a lot of those players that are involved are generally not even producing 3D models. So let's have a look just to give you a visual example of what a BIM model looks like. So as I just mentioned, BIM is not a model itself, it's a process using 3D design and other information. But at the core of everything is a model, so model elements that contain information. So this is our hot water cylinder in our office on Davy Street. And that water cylinder is relatively well defined. So it's got geometric information, like the location of it and the size of it. So it's in a bathroom and the sizes may be approximate or accurate. It contains information that is relevant to design, like mechanical information. It may even have electrical loads, etc. required. It also contains some information that has been picked up during construction or commissioning stages. And it has got information about that is relevant during building operations, like a serial number. So if the cylinder dies, I just look up that serial number in our system and we can service it and find a PDF data sheet, etc. So this is what we would say is a BIM model. A BIM model that is useful from a design stage, from starting during the design stage of a project, over the construction stage, and all the way into the post-construction stage where we need to service our facility. And yeah, that's the same diagram that I've shown earlier, just a bit optimized to show that when we deliver a project using BIM, we need to roll it up from the end. So we need to start to understand what do we need at post-construction to utilize BIM for building operations. And then we need to work our way back to define, all right, the designer needs to put in those models, put some metadata into the models that can then be used and filled out through construction and then handed over for post-construction purposes. So I promise you to keep it all very short. So that's essentially the introduction about what BIM is. Now let's have a look at what the goals are for BIM. And I was trying to find, so there are about 20 or 30 different benefits that BIM can provide, but these are the key ones that I think are relevant to this session tonight. So BIM can and does provide opportunities to reduce rework and waste. So a better designed building and a better resolved building design certainly reduces rework and waste out on site. We can generate or improve the design efficiencies and reduce contingencies. So a good example is on that Hedberg project that we've seen earlier, when we finished our initial design stage. So the concept design stage we had for one of the performance spaces, we had, for the whole project, we had a steel tonnage in our design of about 200 tons of steel. And since we've moved to a BIM process where we could justify and where we had more information about what's actually happening in all of those spaces and improve our design, we brought the steel tonnage that was used on the whole project from approximately 200 tons to approximately 130 tons. So there's, how much is that? Let's say 30% reduction of steel that was used. In particular, if we involve if we involve, for instance, facility managers in building operation early in the process, we can significantly improve life cycle performance. So when you look at that Wellpoint project where we were working with UN Aquaculture, we had the people who were then running on the floor to feed the fish, etc. We had them in our design meetings and we were walking through the buildings, and that's what I'm going to show you shortly. And they gave us immediate feedback on how the building actually performs and where weak points are, where they need better access, etc. If we get facility managers in early, they will actually look at how much energy does this building cost and how much does it cost me to operate this building. So this is something that we usually, or that we not necessarily look into on a on a smaller scale. And I think this is the key point for why I was talking, or why I'm currently talking, is BIM provides us with the opportunity to use a higher degree of prefabrication on projects. And I'm going to give you a quick example with a little walkthrough of one of the buildings. So this is just the facility looking at it from outside. We can now look at the building without the envelope, without the panels showing. And when I zoom in, there's lots of detail. So we have got all the nuts and bolts from the steel fabricator in there. We've got fire hose reels. We've got all the pipes that were installed on the project, all in the right location. And all of this that you see here has been verified and can be handed over, or is handed over to the client, so that they can use this for doing modifications in the building and to run the operations. Let's have a look inside and we can walk through the building. So this is a typical example of what we would do. So we would just get someone in, walk through the building and verify whether everything is thought of and thought through. So one example, when I walk down here, we see that, oops, I shouldn't have fallen down. There's probably a railing missing, but maybe I've just turned that railing off for this example. But what I want to show is, so we see all those nitty little, gritty little details like those pumps here, all the fittings, all the pipe fittings are there. But what the big focus is on BIM to ensure that the different systems that we have here are actually integrated and that they work with each other. So as I mentioned earlier, all those openings where those pipes go through the precast panel here, they need to be defined accurately so that they can be cast during the fabrication of this panel. Then the panel is only going to be lifted on site and installed. So if I just isolate this building, this building component, this precast panel, I can see that there's the opening, and that's exactly the template that the fabricator needs. This is now an example of precast. If that was a CLT panel, a cross-laminated timber panel, that could be fed into the machines. The machines will produce the panel and drill the holes in the exact right location. So that's a good example of where digital fabrication can be supported using BIM and a better coordinated project. I think that's all I want to show the walkthrough here. So, or let's have a look at, so essentially, this is the design model here. This is something that we would call LOD 300. So all the members here, they're resolved. They know exactly where they are. However, the designers, they usually don't create the connections, the steelwork connections here. And we just hand over our design model to the fabricator, and the fabricator takes our design model and refines it further to put all of those connections in that we see here. So early design stage, resolved design stage, including fabrication drawings created. And when we zoom in here, we can again see all the details that are required to fabricate those. And the steel fabricator, and that's something that we are really lucky to have in Tasmania. We've got very, very good steel fabricators that actually use this process for a long time already. So they're modeling all of their steel work, and they just feed this information to their machines, and the machine produces those components. So let's go back to the PowerPoint presentation, and I'm just going to crop this window again. Back. There we go. let's have a look at digital fabrication use cases. So I just already mentioned like wall panels, same applies to floor panels for cross-laminated timber, precast, SIPs, and any other panels that you can think of. Another example would be pipe spooling. So instead of rocking up on site with your individual fittings and pipes, you could prefabricate whole pipe runs, cart them on site and install them. But that only works if you've got a well-resolved digital model that you can trust and rely on. Whole system trays are prefabricated in hospitals nowadays. For steelwork and timber fabrication, I think I gave a good example there for steelwork, but the same applies to timber fabrication. And nowadays, I don't know, there are probably other examples as well, but there's the student accommodation place on Elizabeth Street, and they've installed whole bathroom modules that were prefabricated. However, they were prefabricated in China, carted to Tasmania and installed. So another use case is printing buildings. So there are whole buildings being printed nowadays. But that can only be done if an accurate, reliable model is being created that is fully resolved, and then we can go into fabrication. Whereas nowadays, you resolve most of the issues, send your construction crews out on site and let them resolve all the difficult parts, which then produces a lot of waste, rework, and generally doesn't provide us with an efficient service and design. So that gets me to the conclusion. BIM, why wait? I'm not too sure to expand on all the opportunities how BIM is going to help with local production, but I leave that up to the audience. You may have some interesting ideas there. But I certainly know that if we don't embrace BIM here more, or general better coordinated and digital fabrication processes for the construction industry, we're going to get swamped with components that are fabricated overseas, and the local construction industry is left to install these. So example is those bathroom ports that are prefabricated and sent here. So if this was all too quick, and if someone or a group of people is interested to understand more about BIM, I would be happy to come back and expand on my presentation today. And we may find another session where I can show you more about BIM. So thank you very much for listening. I hope it wasn't too abstract to some of you, and hope we'll get some questions in that Marcos and I can answer, hopefully. Thank you.
And thank you to both of you. You've both done a very good job, and you've thrown up a whole lot of new concepts and new ideas for us to think about. And I can see the two sort of linked together. Klaus's modelling fits in with Marcus's printing, and all it needs is a much bigger 3D printer. Yes, thank you very much. It was very good.
Thank you too.